Hello, my name is Ben Myatt from Kindeva Drug Delivery. I am presenting this work undertaken with my co-authors Steve Stein and Barzin Gavtash on pressure and temperature measurements of current and future low GWP pMDI propellants as measured in the actuator sump. Our industry is embarking on the next phase in propellant usage, akin to the CFC to HFA transition, as new environmentally friendly propellants are investigated. The search for propellants with lower global warming potentials than HFA 134 and HFA 227 has led to research into new low GWP propellants such as HFA 152 and HFO 1234. These propellants all have differences in physicochemical and thermodynamic properties. Atomization efficiency of a pMDI is directly linked to the pressure and temperature of the two-phase propellant formulation during discharge. Higher pressure propellant formulations lead to finer droplets which are easier to inhale and therefore can be advantageous for patients. However, increased pressures can also lead to increased plume velocities, which lead to oropharyngeal deposition. Various other formulation properties, such as surface tension, viscosity, and two-phase sonic velocity, also have significant roles in governing droplet sizes and plume velocity of a pMDI. All of these parameters vary by propellant and also vary with the addition of excipients and co-solvents, if present in a pMDI formulation. There is still a significant amount to learn about how some of these physicochemical properties and thermodynamic properties govern the droplet sizes and velocity of the spray emitted by a pMDI. In this work, we developed a new instrumented pMDI actuator sump, building on previous works within our research group which have been published in the literature, with the goal of measuring pressure and temperature in the sump of a pMDI actuator. The stem block was removed from a standard Kindeva drug delivery actuator and instrumented with a fine wire thermocouple. The bead was placed in the middle of the sump volume. A pressure tapping was introduced at the bottom of the sump, which was mounted on a test rig fixture. The fixture incorporated a mount for a Kistler piezoelectric pressure sensor. The void volume between the sensor and the sump was minimized in design, and during testing was filled with a coupling fluid to transfer the pressure in the sump to the sensor diaphragm. Placebo aerosols containing current and future potential pMDI propellants were fired through the instrumented actuator sump. The thermocouple signal was amplified using bespoke equipment, and the output, along with that of the pressure sensor, was logged with high speed and high resolution by a Kistler lab amp. In the figure on this slide, you can see the pressure profile of the two-phase propellant formulation as it flows through the actuator sump through time. A very sharp rise of pressure is initially measured as fluid, firstly vapor and then vapor-liquid mixture, rapidly flows from the metering chamber into the sump via the valve stem as the pMDI is depressed. As the sump fills with liquid, rich propellant, the pressure of the formulation in the sump rises to a peak. The peak pressures measured in this work correlate exactly to the saturation pressure of each propellant at that measured temperature. After the pressure peak, further evaporation of the liquid propellant creates more vapor, which expels the two-phase formulation from the actuator sump and causes self-cooling of the formulation. Thus, the pressure in the sump reduces. The pressure signal, and therefore spray duration, varies by propellant and vary broadly in line with vapor pressure and density properties. The vapor pressure is the driving force by which the two-phase vapor-liquid mixture is expelled from the actuator. The higher the vapor pressure, or the lower the propellant density, the shorter the plume duration. HFA 152 is the lightest propellant and has the second highest vapor pressure of those measured in this work, and the shortest pressure signal that's measured. HFA 227, by contrast, has the highest density and the lowest vapor pressure and the longest pressure signal. The figure on this slide shows the temperature profile of the two-phase propellant formulation as it flows through the actuator sump. The temperature profiles are all very similar in trend, showing an initial sharp drop in temperature as cold vapor flows into the sump. As liquid, initially at ambient temperature within the metering chamber, flows into the sump, there is a brief temperature recovery. The liquid expands and evaporates, producing further vapor and self-cooling, reducing the temperature of the formulation in the sump. The minimum temperatures measured at the end of the event correlated exactly with the saturation temperature, also known as the boiling point, of each propellant at ambient conditions. The temperature in the sump remained at the saturation temperature until all of the liquid in the sump had been evaporated. Interestingly, despite a similar saturation temperature to HFA 134, the HFA 152 propellant exhibited the sharpest initial temperature drop within the actuator sump, being noticeably colder than the other propellants, and remaining so through the first 100 milliseconds of the spray event, over which the majority of the metered dose is emitted from the device. The latent heat of vaporization and specific heat capacity properties of all of the propellants we tested vary. In the case of HFA 152, they are both much larger than those of HFA 134, and this could be a contributing factor to the differences seen. So to conclude, in this work we measured pressure and temperature in a pMDI actuator sump during a spray event for various current and potential future pMDI propellants. We know that pressure and temperature of a pMDI formulation are important parameters that govern droplet size and velocity of a spray emitted from the device. Pressure and temperature profiles were similar for all propellant formulations surveyed. Peak pressures measured correlated exactly with propellant saturation vapor pressures at the associated measured temperature. Final minimum temperatures correlated exactly to the saturation temperatures of each propellant at the ambient conditions. HFA 152 exhibited a much sharper temperature drop than the other propellants measured through the main phase of the spray. And with that, I thank you for taking the time to listen to this presentation and your interest in our work.